So welcome back. I think we finally got all the electronics figured out. And so what I'm going to do is pick up in the middle of lecture 2 where I left off last time. And questions are always welcome, but let me just review what we did last time and look ahead. So what I did last time was I looked down at the bottom in the stack, well, I'll tell you what I mean by stack, of all the hardware, and I tried to convince you by showing you some data. So as a scientist, I had to show you data. I wrote very simple programs, and I measured how fast they went. And they had very complicated behaviors, when you ran them as to how fast they went. And so the takeaway from that is that we need some simple mental model so that when you write algorithms and organize them, and that's true, this was true for a sequential machine, it'll certainly be true for a parallel machine too, so that you need to think about what are the expensive operations so that when you design an algorithm and write code, you will, with high likelihood, have a code that runs fast. Now, if we're lucky, we will actually have a theorem that says that here is the optimal way to organize your code that will provably minimize the amount of the number of expensive operations, which is to say moving data to and from memory. In the case of matrix multiply, which is the example that I did last time, we had such a theorem. And that theorem said that no matter how you take those n-cubed multiplies and adds, which the classical matrix multiply does, you have to move at least a certain number of words between the big memory where the matrix fits and the tiny little fast memory of size capital M where it doesn't all fit. And you have to keep moving things back and forth. And the answer was you have to do at least n cubed divided by the square root of M, the cache size, moves. And this is sort of an ongoing research area trying to prove theorems like that and using that to design optimal algorithms. We just gave that one illustration. We'll have a lot more as the semester goes on. So the other thing that we're going to be doing is asking ourselves, if you have a high-level application, you want to just do signal processing or model the climate or whatever, how do I take that and recognize how to decompose it into these well-understood algorithms at the next level, into matrix multiplies or FFTs, or we're going to have a list, and you've seen that list before. And so that's going to be another level of abstraction, not entirely today. This is sort of for the rest of the semester. And then there's one more layer that we're going to be spending time talking about, which is what are the software tools that let us do all this without starting from scratch. And so in principle, what should that software do? It should let us write software that's both efficient and productive. So what do I mean by that? Efficient means the code runs fast, and productive means you can write it fast. That you don't have to spend hours or days or years writing assembly language, you can write it very quickly. And so both of those are goals, and these are the layers in which most people work when you try to write, solve a problem. You have an application that you want to solve. You will decompose it into algorithms. You will ask, what are the best software tools that let me, map it onto the hardware as quickly as possible, and then hopefully that software will hide most of the details of the hardware. But not necessarily, which is why we're talking about all those different layers throughout the course of the semester. So any questions about that before I continue? So what I want to do is tell you a little history of how we came to matrix multiply, because that's not what people did in practice. But it has become so important that there's now an industry standard. Everybody agrees on how to spell matrix multiply, no matter what computer you're on, so that you can call the same subroutine and you'll be pretty much guaranteed you'll get the best implementation. Now, we actually beat significantly how well, for example, Intel does matrix multiply. That's another story. We'll come to that later in the semester. But there are two there's an industry standard, and here are two websites which give you the non-optimized sort of public version of the codes and describe all the interfaces. And so how did this come to be? Well, historically, back in the 70s, people said, okay, we need to do this, come up with a standard, and a committee got together and they defined not matrix multiply, but operations on vectors, things like dot products or Saxby's. Saxby is short for AX plus Y, which is the operation there, so a scalar times a vector plus a vector. And that was good enough at the time, but let's ask ourselves, would that satisfy our modern constraint that you have to have a lot of data reuse, that you need to have a lot of computational intensity, which is, just to remind you, that's the number of flops divided by the amount of data it works on. So if you think about a dot product, just to give a simple example, how many flops does it do? Well, you have n multiplies and n adds. The number of flops f is 2n, n the length of the vector. How much data does it have to move? You have to read x and read y out of memory, so that's 2n, and so that ratio is 1. And so you do on average one floating point operation per memory access, and so there's no reuse possible at all there. Now you might ask, why did the committee bother to get together to standardize things which should be like one loop? And the reason was that in order to make it was both speed and correctness. So for example, this looks like a very simple loop. You know, you do alpha times x sub I plus y sub I. But if you, to map to the architectures of the day, you might need to vectorize that. And that would involve writing some assembly language at a low level, and so they wanted to hide that all from you. But the other reason was getting the answer right. So how about computing the 2 norm of a vector? So that's the root sum squares. So what's the obvious algorithm? You sum the squares and you take the square root. So why is that wrong? Why can that obviously get the wrong answer? Well, imagine that one of the vector entries is just a little bit bigger than the square root of the overflow threshold, the largest floating point number in the machine, so that when you square that number, you'll either crash the machine, that's what happened back then, or you'll get an infinity and you'll get the wrong answer, even though the final answer itself is a perfectly representable number. The same thing can go wrong if all the numbers in the entry are too small and they underflow when you square them. So they wanted to hide all the details, and so they did that. That was good enough for a while, but then machines got a little bit more complicated and the memory accesses became more expensive. So the committee was met again, and they invented what's called the BLAS2, and those were matrix vector operations. So they worked on n squared data instead of order n to the 1 data, and it included things like matrix vector multiply and solving triangular systems of equations. I think there were about 25 different operations in all that they standardized on. So let's ask if they improved the memory accesses there. So for multiplying a dense matrix times a vector, so how much data do you have to move? Well, it's an n by n matrix, so you have to read in n squared items. That's sort of the biggest thing. And then you do 1 multiply and 1 add for every one of those matrix entries. So you take the ratio 2n squared divided by n squared, and you've made progress. You've increased the computational intensity from 1 all the way up to 2. So that was progress in the day. But it also decreased a lot of loop overhead and other things that you would have had if you'd have just called a dot product inside a loop. And this was definitely faster than the BLAS1. And I'll show you some data on the next slide to confirm that. But finally, that still wasn't good enough, so the committee met one more time, and they standardized the BLAS3 back in the mid-'80s, and they finally went to matrix operations, of which matrix multiply is the canonical example, but there's 9 different operations that they did. And now, finally, you get the improvements that I was showing you before. You're doing order n cubed operations on order n squared data, so the computational intensity has the potential to get as large as n, even though there's some theorems that say you can't quite get there, but it can be a lot better. And so once all of these were available, everybody went back and said, okay, can we redesign all the higher level algorithms that use these, things like Gaussian elimination and solving least squares problems and eigenvalue problems. And I was and am still a member of that team, and we produce these libraries called LAPACK and ScalaPack, which spend all their time not doing, adding a multiple of 1 row of a matrix to the next row, which is how we learned how to do Gaussian elimination. And sophomores, you spend your time doing matrix multiply to the extent possible. And there's a public domain version of these, and again, all the vendors take them and tune them a little bit, especially for their particular architectures. And now we know, actually, that you can do asymptotically better than we thought we could. Even back then, when we said, okay, at that point, if you spend all your time doing matrix multiply, that must be optimal. Well, it's not. And so but that'll come in a later semester, a later lecture in this semester. Don't worry. So let me just show you some performance data. And so this is on an old machine. You can see it's a 266 megaflop peak machine, so it's really quite old. The horizontal axis is the size of the data, and the vertical axis is performance, so up is good. There's the peak. There's the speed of the BLAS3, matrix multiply, and it's getting close to peak. That line is BLAS2, and that line is BLAS1. So you'd clearly like to spend your time doing that. The other way to remember what's BLAS1, 2, and 3 is how many operations they do. BLAS1 does order n to the 1 operations. On an input of size n, BLAS2 does n squared, and BLAS3 does n cubed. So that's, besides being the numbers of the committees, that's what it does. So let me show you some more data, just to show you this picture is standard across lots of machines. And so here are lots and lots of different platforms, and each pair of vertical bars is comparing the speed of matrix multiply, that's dgem, that's the standard name for it in the library, versus dgemv, which is the standard name for matrix vector multiply. The vertical axis is megaflop, so up is good. And you can see how many times larger the matrix-matrix multiply bar is than the matrix-vector multiply. So across all these different platforms, you'd obviously want to be spending your time doing matrix-matrix instead of matrix-vector. Now these are for square matrices, and your performance may differ significantly if you have rectangular matrices or whatever, but there's still large benefits to be had. Now, so far, everything I've told you has been how to optimize when you have two levels of memory, a big slow memory and a small fast memory of size capital M. But real machines have lots of levels of memory. And so the question is, what are we going to do about that? You can't just think about one level, because you might have L1 cache and L2 cache and L3 and DRAM and disk and so on and so forth. And what you really need to do is minimize the communication between all pairs of adjacent levels. And so the question is, how are we going to do that? And so the algorithm that I showed you last time, which I'm not going to repeat right now, but let's remember what it did. I had 3 nested loops, but the innermost loop didn't just do a multiply and an add. It multiplied 2 B by B submatrices and added it to another B by B submatrix. And choosing B was, a tuning parameter, or we sort of said it's about the square root of the cache size. All those 3 B by B blocks had to fit in fast memory at the same time. But what if we had more levels of memory? So if we had one level, then that's the naive algorithm. That's 3 nested loops. The algorithm I just told you about, 3 nested loops and then another matrix multiply, that matrix multiplies another 3 nested loops, so that's 6. If I had another level of memory hierarchy, I'd have 9 nested loops, because I'd have to block the innermost loop again. And you can see this code is going to get messy and complicated. And so what people discovered, because this was a frustrating problem, is that there's another approach, which in theory works no matter how many levels of memory hierarchy you have. And it's optimal, and you don't have to know the sizes or the number of levels of all the caches. So in that case, it's called a cache oblivious algorithm. So it's oblivious both to how many layers you have and to the sizes. If I did it this way, I'd have to know the size of every layer, which is going to be a mess. And so let me show you how the algorithm works. And it's based on recursion. And so let me write out in all its glory detail the formula for multiplying two 2x2 matrices. So think of all of these as being scalars, and there are all the 8 multiplies and the 4 adds that it takes to compute this 2x2 matrix. Now it turns out that this formula that I've written here is completely true, whether or not each of these guys is a scalar, so a 1x1 matrix, or they're n over 2 by n over 2 matrices. So in other words, this is an n by n matrix, and that's just the upper corner of size n over 2 by n over 2. These formulas are still correct. So in other words, this dot is an n over 2 by n over 2 matrix multiply, and that's an addition of them, and so forth. So what I've done is I've broken up my problem of n over n by n matrix multiply into 8 smaller problems of half the size. That's divide and conquer. I'm going to write it as a very simple subroutine, and if you've taken computer science courses before, it's very natural to have a subroutine whose name here is RMM, recursive matrix multiply, that calls itself. That's a perfectly correct thing to do. So what am I going to do? I'm going to pass in 2 matrices of size n by n. If n is 1, that's the simplest case. They're just numbers, scalars. So I actually do the work. I do the multiply. Otherwise, I call myself recursively to multiply these 2 matrices of half the size. And for each of these dots, I have a subroutine call, and then I add them. So that plus is actually adding 2 n over 2 by n over 2 matrices. And so that's the algorithm. And so let me now convince you on one slide that it has the same arithmetic complexity. It's still going to do the same 2n cubed floating point operations, but it also hits the lower bound and how much communication it does. So there's the code again, and all I have to do is write down 2 simple recurrences to count a of n, that's the number of arithmetic operations, and w of n, that's the number of words moved between fast and slow memory. And so it's a recurrence, so the amount of work to do n by n matrices, I have 8 problems of half the size, so 8 times the number to do half the size. And then I'm doing 4 additions of n over 2 by n over 2 matrices, so that's that term. Those are all the additions. And you can solve that, you write it out. It's a simple geometric sum, and it turns into 2n cubed. You're doing exactly the same operations that you'd normally do, just in a different order. So let's write down the recurrence for how much data gets moved. So that's w sub n. And the simplest thing to do, if you don't optimize at all, is that when you call this problem on half the size, you'll move w of n over 2 words. That's what w means, but you'll do it 8 times, because each call is done that way. And then I'm going to have this addition, so I have to read a matrix, read a matrix, and write a matrix. So that's 3n over 2 squared, and I'm doing that 4 times. So anyway, I get some number times n squared. And that recurrence looks almost the same as this recurrence, except the constant's a little bit different. The thing is, this recurrence doesn't go all the way down to 1 by 1 matrices. It stops at a certain point. Because once the 3 matrices fit in cache, once 3n squared is less than the size of the fast memory, then the recurrence is over. I read everything into fast memory. They just stay there, and there's no more memory activity until I'm completely done. So now when you write it out and solve it, it's a geometric series again, but it's truncated, and the answer turns out to be the optimal answer, which is n cubed, the number of flops, divided by the square root of the fast memory size. And I only needed to know the fast memory size to do the math, not to write down the algorithm. So this was optimal no matter what m fast was. And it's also, if I have more than one value of m fast, if I have multiple levels of memory hierarchy, it's all true too. So this, this, needless to say, made people very happy when it was discovered as a good idea. But unfortunately, it doesn't solve all your problems. I mean, it works well sometimes. So for one thing, to make this practical, you can't recur all the way down to 1 by 1 blocks. You'd be completely overwhelmed by all the cost of the subroutine call overhead. So in practice, you decide, oh, it's 64 by 64. It fits in the cache on this particular machine. I'll just call the optimized code for that. So you have to cut it off there somewhere. And so you have to pay attention to that. So you can't completely ignore the memory hierarchy. And so people have tried to do this before, and there's a paper I'll just point you to where they tried to optimize it as well as they could, and they got within 2/3 of the peak machine speed compared to the 90% that the hand-tuned machine code would have done. Now, the thing is about matrix multiply, you may be, you don't want 2/3 of peak, you want the 90%. Somebody else has already figured out how to do it. But this idea of cache obliviousness works for a lot of other algorithms where you might be perfectly happy to get 2/3 because there is no library around to use instead. So this, we'll show you lots of other examples of cache oblivious algorithms. Anyway, there's just lots of details to get it done right. We've been experimenting here with cache obliviousness in the parallel case. So it's supposed to be parallel oblivious. No matter how many processors you have, we sort of distribute the work out. And I'm going to tell you about parallel matrix multiply later. Our algorithm is called KARMA. It's communication avoiding recursive matrix algorithms. And that's where we go significantly faster than the vendor's hand-tuned BLAS. But I'll save that for a later lecture when we talk about the parallel versions of these algorithms. So that's one part of the tuning space. Here's another one, which is what data structures should I use? So the one, I haven't mentioned the data structures yet, so we've been assuming implicitly that you store matrices in kind of the obvious way, either column-wise or row-wise. So if it's row-wise, which is what you get in C, all the rows of the matrix are, one row of the matrix is in contiguous locations, and then the next row is in the next contiguous locations. But that's not a very good data layout for the particular algorithms I want to use, because what does that recursive algorithm do, or what does the blocked algorithm do? It wants to grab a B by B block of the matrix, pull that into cache, and then work on that B by B submatrix. So I don't want to grab a whole row or a whole column. I want to grab a block. And so that is, ideally, that block would be stored in one contiguous location in memory. So I don't have to keep touching the memory over and over again to get B different rows or B different columns. And so what we'd like to do is have a data structure which had the property that whenever you grab a square subblock, it's going to be ideally be all in one contiguous block of memory, or maybe at worst, order 1, 4 blocks of memory. And so here's the trick to make that work. And if you ever had a course in mathematical analysis and learned about space-filling curves, then the idea is very similar to that space-filling curve idea. So what I'm going to do, so here's my matrix. I'm going to break it up into 4 subblocks, which I have red boundaries. And I'm going to store the northwest corner first, all together, then the northeast corner, then the southwest corner, then the southeast corner. Right? So this block will be all together and so forth. And I've drawn this Z shape there to indicate the order in which those blocks appear in memory. So what do I do about this upper block? I'm going to do the same trick. I'm going to do the same idea recursively. I'm going to break it up into 4 blocks of half the size. I'll store the northwest first, then the northeast, the southwest, the southeast, so it's another little Z-shaped ordering. And all the other blocks are the same, and I keep doing that recursively, maybe not all the way down to 1 by 1, but pretty far. So now, if I do want to grab, for example, that particular subblock of memory, it sits in exactly one contiguous set of locations, and I'm very happy. What if I want to grab that slightly larger subblock, which goes up to that corner? Well, you can see it'll be residing in 4 contiguous blocks of memory, and maybe that's not so bad, as opposed to, the number of blocks of memory being proportional to its dimension. And so this has a great advantage. This works well for, the recursive layout works well for any cache size. It's oblivious to that. Now the disadvantages is that, as a user, do you really want to figure out where to put all the matrix entries? So if I say, please get a sub ij, where the heck is it? There's sort of a complicated formula for that. And so what people often do in practice, and this is a tuning parameter, is that the user hands you the matrix in the user's favorite layout, which is probably going to be row-wise or column-wise. The subroutine then converts it to this format, does all the work, and converts the answer back. And the chances are that the little bit of work to do the conversion, that's called copy optimization, is going to be well worth it. And that will be, the extra cost of that will be overwhelmed by the benefits you get from doing all the n-cube work on this particular data structure. So that's yet another low level of optimization. Okay, so are there any questions so far? So all of the algorithms I've told you about up to now have been the classical variations in the classical 3-nested loops. So we're always been doing n-cubed multiplies and n-cubed adds. But there's no reason we have to do n-cubed. We can do asymptotically fewer. And so let me tell you about the first algorithm that was discovered that did this. It doesn't do n-cubed operations. It does n to the 2.81 operations. And I'll tell you where 2.81 comes from in a moment. But as n gets larger and larger, this can be arbitrarily faster than the classical n-cubed algorithm. And so here's the idea of how it works. And again, all I have to do is explain how to multiply 2 by 2 matrices, and then I'll use that idea recursively. So just imagine each of these things is a scalar. So it turns out that if I form these linear combinations of the entries of the original matrix, and then do 7 multiplies, not 8 multiplies, these are 7 multiplications, I get these 7 intermediate products. And then magically, if I take these particular linear combinations of those 7 intermediate products, I get the answers that I want. All the extra terms that I would get, for example, A22 times B11, that shouldn't appear in the answer, it all magically cancels. And I get the answer that I want at the end. And this is called Strassen's algorithm. So let me tell you why this is arbitrarily faster than the classical algorithm. So I'm going to write down the recurrence, because the algorithm is going to be recursive. Remember recursive matrix multiply, where I called the same routine 8 times in the inner loop? I'm just going to use this exact same idea, except now I'm going to call myself 7 times in the innermost loop, because there are only 7 subproblems of half the size. And so if I write down the recurrence for how much time it takes, so this is the cost, so think of counting floating point operations, I'm going to solve 7 multiplications of half the size. That was 8 in the old algorithm. And then I do a lot more additions, right? If I count them, I'm doing 1, 2, 3, 4, 5, 6, add them all up. There are 18 additions, right? So this term is certainly a lot bigger. I just did 4 before. But when you solve it, it's a geometric series. The solution turns out to be proportional to n to the log base 2 of 7. That's where the 2.81 comes from. If I did if that 7 were an 8, that 7 would be an 8. I'd have the log base 2 of 8. That's where n cubed comes from. And so this is asymptotically faster. So the larger the problem, the bigger the potential speed up. And but of course this constant shows up too. That makes it a little bit slower on small problems. And so where exactly, how you do it is going to be a tuning problem. Now, it's natural to ask ourselves how much, it's not just important to do less arithmetic, the whole point is to do less communication as well. And so we can ask ourselves, is there a lower bound on how much data this algorithm has to move between main memory and slow memory? And it turns out there's a theorem there too, and here it is. It's proportional to the number of floating point operations, so n to the now log base 2 of 7, used to be n cubed. And in the denominator, it's not m to the 1/2 anymore, it's m to something smaller, m to the 0.4, turns out to be. It's that particular formula. And I'm pleased to say we were the first ones to prove this, and it won a Best Paper Prize a few years ago. And that recursive algorithm actually attains it. And there's actually a parallel algorithm which attains an analogous lower bound, and we'll talk about that later. And this currently sets the world's record for the fastest matrix multiply implemented on any parallel machine. And so we will get there later in the semester. But what I want to do is give you a little history of, so Strassen was the first. He was actually, I think, a visitor here back in the 60s when he discovered it and published it and became very famous. But ever since 3 was reduced to 2.81, people have been trying to make that exponent smaller. So let me tell you what the history of that exponent is. For many years, people worked on it, and back in 1987, the world's record was reduced to end of the 2.376. And that stuck around until about 3 years ago. And then there was a new world's record, and I think I may have mentioned I had the honor of being in the seminar room upstairs in the WAS when the student, Virginia Williams, a postdoc here, announced her new result, and she got the exponent all the way down to 2.373. So you can see people really want to get that exponent smaller. And that's currently the world's record. And now, practicality, I'll come back to that. Okay. So now it turns out that the lower bound on how many words you move can also be extended to some of these algorithms. There's some technical assumptions. It's an open problem to remove those technical assumptions. But again, you get n to this power divided by the m, the cache size, to some power that depends on this. And that is, by doing the recursive algorithm, that should be attainable. So there is the possibility of an algorithm that goes all the way down to n to the 2 plus a little bit, plus epsilon. And so there was this very beautiful paper written back in 2003 where this algorithm was re-derived by using group theory. So this coming up with this algorithm turns into a group decomposition problem. So if you're a mathematician interested in group theory, then I certainly recommend this paper. So people are now still busy looking for new groups and decompositions in order to lower that exponent. Now, one of the obstacles to the take-up of these algorithms, besides the fact they're very complicated, has been, do they get the right answer? So that means, and of course in exact arithmetic they get the right answer, but when you do floating point arithmetic and make round-off errors, people were doubtful. And so there's been some work on showing that you can modify them slightly so that the round-off errors are asymptotically about the same as the classical matrix multiply that everybody is used to. And the other obstacle is that besides Strassen, which is faster in practice, you may need, the constants hidden in all these big O's are really kind of unrealistically large. So Strassen is useful, but the other ones seem not to have been. So you may wonder why Strassen is not the standard in all these different libraries, and there's sort of a funny reason for it besides that numerical stability, and that's because using Strassen is forbidden by the top 500 list, by the competition that every 6 months who has the world's fastest computer. And the reason they forbid it is that the way they measure how fast a computer is that they want to compute floating point operations per second. So the second, the runtime, they measure that, but what's the numerator? The numerator is how many floating point operations you do, and so that's going to be 2/3 n cubed, whatever the classical implementation of Gaussian elimination does. If you use Strassen or some variant hybrid, who knows what the numerator would be? And so to have a fair comparison, they always put a 2/3 n cubed in the numerator. And so if you use Strassen, you could go faster than the peak speed of the machine. And so that doesn't make sense, so they forbid it. And so all the teams at the supercomputer companies don't bother optimizing Strassen simply because they want to win the top 500. It's silly, but that's the way the world is. Okay, so what I want to do now is tell you about tuning code in practice, giving you some low-level hints, which you will find useful in your first programming assignment. Whether you want to use them at all for the rest of the semester or your career is up to you, but I want you to at least see them once. And so there's going to be a lot of variations to try. And so in practice, one thing that people have done is to say, there's so many different combinations, why don't I just write a program that tries them all? And so this, in fact, started in this class a long time ago, because we've been using this matrix multiply assignment for a long time. And at the end of the week, you will do the same thing. You'll race against not just one another, you will race your matrix multiply against the hand-tuned code from the vendor. And for many years, nobody ever beat the vendor. I mean, the vendor was fast. But there was one year where 2 teams beat the vendor. And so that got the teaching assistant very excited. And so what he did was he went off and tried to figure out what the students did. And it was complicated. So he built an auto-tuner, which tried all the different combinations that the students did. And that led to a project called FEPAC, and which was a prototype auto-tuner, portable high performance in C. that led to another project called Atlas, where they did a much more thorough engineering job of trying combinations and more performance. That was eventually adopted by MATLAB, and basically auto-tuning is the way many of these basic codes get written. So, for example, for the FFT, if you ever use an FFT, it will almost certainly have been auto-tuned. It turns out that if you look at the literature on how to do FFTs, the classic one that we teach students is called the Cooley-Tukey divide and conquer FFT. That was the first paper. There have been 100 since then on how to divide an FFT into smaller problems and do divide and conquer. And so the auto-tuner that people built has incorporated in it all 100 math papers about how to do divide and conquer in the FFT, and it just tries all the possible combinations. You don't want to do that by hand. And so, and I'm pleased to say, we just found out over the weekend that our paper, which we wrote 17 years ago, just won a Best Paper Prize for the, one of the most important papers published in that conference in the last 25 years, because it sort of led to all of this, helped lead to all this other work in auto-tuning. So you don't need to do auto-tuning for your first assignment, but people have in the past, so you're welcome to give it a try. But I'm telling you all this because not every code will have an auto-tuner, and if you really want to get peak performance, you might want to do some of this by hand, up to you. So let me give you sort of a tour of what these tuning space is like. So the first one is, what are the right block sizes? So I said the theory predicts that they should be square subblocks, and they should be all, you need 3 of them, one for the 3 matrices A, B, and C, and they should all fit in fast memory. And so that sort of gives you an idea of what to look for, but in practice, it's, especially if your memory size are the registers, you may only have a very small number of registers, and then you can't just divide by 3 and take the square root. It's a much more discrete search space. And so I'm going to show you some data now in a moment where about what the performance actually looks like. And so people have tried to take that model that I showed you, the predicted B by B block sizes, and put in more details about the architecture and try to tune it to predict it more accurately. It's pretty hard. So let me show you some real data. And so this is what the tuning space looks like. And so each of these squares is color-coded. It represents a different block size. And it's color-coded by how fast it went, down from 100 megaflops, this is an old machine, up to about 600 megaflops, which is red. And this is tuning for just the registers, right? So that's sort of the top level of the memory hierarchy. And this particular machine only had 16 registers. So that means that we can't have blocks that don't fit in 16. And so all of these numbers up here are where this block times that block is bigger than 16. So we didn't even bother searching up there. So what are the block sizes? There are 3 of them. So because it's not square anymore, it's rectangular. So it's N0 by K0, which happens to be 1 in this slice through the design space, by M0. So we have these 3 blocks, 2 blocks, they all have, but they have to have matching parameters, dimensions, so that's what it is. And so there's 1 by 1, and there's 6 by 1, and so forth. And so we just tried them all. This is what the auto-tuner does. And the winner is 3 by 2. It's the darkest color by far, and nearby it's whatever else. So why is the answer 3 by 2? I don't know. It's some complicated function of all of the architecture and how the SIMD instruction set gets generated and the compiler and all this sort of stuff. And all we care about is that the answer is 3 by 2. We don't actually care why. I mean, at least at certain level, depending on what your goal is, right? If you're a computer architect, you might care deeply about why the answer is 3 by 2. But if you just wanted to multiply matrices as fast as possible, you just want to know the answer. You want all of this hidden in the subroutine. So this is one example of that search space. So let me tell you how well the auto-tuner does by searching not just at this level, but by all the other levels. So this is the Atlas auto-tuner, which was a follow-on to FEPAC. And these are many different platforms. So each triple of bars are comparisons of speed on a different platform. The red bar is the vendor's hand-tuned, optimized, dense matrix multiply. This is 500 by 500 matrix multiply. The blue is the auto-tuned code. And the brown is the naive 3-nested loops, which is always much less. And so you can see sometimes the auto-tuner wins and sometimes the vendor wins. And on this platform, there was no vendor code, so you only had the auto-tuner code. And so this is one of the tools that people have, as I mentioned, developed not just for matrix multiply, but for FFT and all of signal processing, and we'll have more lectures on that later. Okay, so now let me give you a list of all the different low level of optimizations, which you can choose to try or not in your first assignment. It kind of depends on how much, how you like to spend your spare time. And so I just want to give you a tour of what are the options. So the first one is tiling or blocking for registers. And that basically is, I've already shown you that picture. That was the colorful chart where 3 by 2 was the winner. So what do I mean by that? So when it's that small, you don't actually have a loop. You don't have a loop from 1 to 3 and from 1 to 2. You actually unroll the code. All 6 combinations are written out as separate lines of code. And because it's not worth having the overhead to increment the indices, you just unroll it. So that's how that tuning is done. Then there's also tiling for multiple levels of cache, and I mentioned the cache oblivious approach, but you could also have 3 more nested loops for every layer of cache and the translation look-aside buffer, which is what deals with disk. There's also exploiting fine-grained parallelism. How do you give a hint to the compiler that there's actually a lot of parallelism in your inner loop? Depending on how you the details of how you write the inner loop, the compiler may be smarter or have a better guess than otherwise. There's a lot of flags on compilers. In fact, some compilers have a flag which is minus matmul. And that's basically a flag that says, I'm telling you this subroutine is actually matrix multiply, so go ahead and replace it by your favorite implementation. And that's cheating. You're not allowed to use that on your assignment, but it does exist on some compilers. And there's lots of web pages with more information about this stuff. I just want to give you a quick tour. So here is one thing you need to do to tell the compiler that there's actually parallelism in your code, because it may assume that it's not. So here are 2 lines of code which should be completely independent of one another, right? So I mean, you've written the code. There's array B, there's array A, and what could these possibly do to interfere with one another? Well, the thing is, the compiler does not know that array A and array B do not overlap. I mean, you know that because you wrote it, but it doesn't know that, right? A sub I could actually be the same location as B sub I plus 1, which would mean the compiler would have to finish this line of code before it could start executing that one, because this number is actually that number. So that's called a false read, this value, after write that value hazard. And so how do you tell the compiler that, no, I really mean they don't overlap? There are several ways to do that. And I should say this is only a problem in C. Fortran will assume they don't overlap. Fortran assumes they don't, and C assumes they do. So you could change the code this way, and you could declare 2 floats, make up 2 new scalars, set them equal to these 2 numbers, and now these clearly don't overlap. That's an array, that's a scalar. Those can be done in parallel. So that's one way you can give a hint. There are also pragmas, and sometimes you can sort of give a hint to the compiler that 2 arrays do not overlap, and that kind of depends on special flags in the compiler. So here's another example, which is a convolution, which is a little bit different from matrix multiply, but it shows what you can do. So here I have an input array, I'll call it a signal, which is a long array, and I have an output array called result. And what I want to do is take every 3 consecutive results of the signal and take a linear combination with these 3 fixed constants, so filter. So this is the first value. The second value of the result will be these same 3 constants times signal 1, signal 2, signal 3, and then the next 3 values of signal. There's a window of size 3 which marches along the array. And so what you'd like to do is make sure the compiler does not go off to memory and grab, every time it goes through this inner loop, grab these values of filter from memory again. These are really constants, right? They should just be read in once, kept in registers. And so one way you can do that is to define 3 new scalars, F0, F1, and F2, to be those 3 array entries. And now the inner loop is quite clear that this dot product of length 3, you need no more memory accesses to get those 3 scalars. So here's another way. So that's one level of optimization. Let me go a little bit farther, because there's a lot of parallelism here, potential parallelism. So that's another way to say it's please don't go to the memory. It actually should sit in a register. So let me try to expose instruction level parallelism. So this is the same program. I'm still doing the same tiny convolution. But what I'm going to do is unroll the loop by 3. So my inner loop here is now going to compute 3 consecutive entries of the result. And so 0, 1, 2, and then 3, 4, 5, and so on and so forth. And so what I'm going to do is I'm going to begin by reading in the first 3 signal values, S0, S1, and S2. those are the first three array entries. So now I come into the inner loop, and the question is, what can I do in parallel? What arithmetic can I do while I'm going off to memory, the slow stuff, and grabbing the next input, the next value of the signal? Well, what do I have available in this first line of code? S0 is not available yet, but I still have S1 and S2 because they're left over. So I can do that multiply and that add in parallel. And then S2 is available down here, so there's another multiply. So I have three multiplies and an add that can be going while I'm waiting for S0 to show up. So what happens after and the hardware will automatically try to do all that at the same time for you. So what happens after S0 shows up? Well, I'm going to multiply it there, there, and there by three different coefficients because it appears in three different values of the convolution. So I can have these three multiplies going on as soon as S0 shows up while I'm waiting for S1. Once S1 shows up, I can do two multiplies, and then I have to wait to get S2 for the final result. And so I could obviously, this is a pipeline. This is called pipelining. We saw that example last time. Here the pipe is only of length 3. I could have made it longer, but that's the general idea. So here's another way to sort of reorganize the inner loop to expose possible parallelism. So most machines can do more than one floating point operation at the time. How should I write the inner loop to tell the compiler that it's okay, you should try to do these things at the same time? So suppose that I have an independent multiplier and an adder, and they can run at the same time. Then it's pretty clear that these two lines of code can run together, right? Because one uses the multiplier, one uses the adder. So that's one cycle if I'm lucky. And then this one is another cycle if I'm lucky. But what if I have, like on most modern machines, I have what's called an SIMD unit. I have a single instruction that can do two multiplies and another single instruction that can do two adds. I'd really like to do these two multiplies at the same time and then launch these two adds. So what I should really do is order these in a different way, the multiplies followed by the adds. And what an auto-tuner could do is simply try all the different permutations of this and pick the fastest one because you don't necessarily know for your architecture. And so that is yet another kind of optimization. And then I already mentioned copy optimization, where what I need to do is find a square subblock of the matrix. And so this is in fact incorporated into Atlas. What Atlas will do is it wants to multiply a B by B submatrix. It will grab it from memory, copy it into a separate chunk of memory which is all contiguous. So for example, it's going to store it as this is a 2 by 2 block. This is what's contiguous. This is what we want. This is the original layout. So it will grab these four numbers and store them that way, and then it will do all the work in the inner loop on that data structure, and then copy it back into the output data structure. And that's extra work and extra memory to copy from this format to that format, but it makes the inner loop run so much faster that Atlas wins, and so that's why they do it. And so a little bit of extra memory can help you go faster that way. Okay, so these are things you may try or may not try, but they're all things that happen underneath the covers at some level. So let me just sort of talk about other algorithms briefly. I mean, I've been using matrix multiply as the canonical example, but these ideas show up everywhere. And all algorithms have this notion of computational intensity. Just to remind you the definition, the number of arithmetic operations divided by the number of words moved. The bigger the better. The bigger it is, the more opportunity we have to increase locality, reuse stuff that we bring into memory, so we minimize data movement. And there's a lot of, and for matrix multiply, which is incredibly well studied, we sort of think we know how to do that. It turns out that there's lots of other open questions and algorithms. We have some recent progress where we've extended these matrix multiply tricks to kind of arbitrary code with nested loops and arbitrary array references. But how to attain it how to attain those lower bounds, we don't know. So there's lots of open questions there, and we'll get to them later in the semester. So let me finish lecture 2 and then go on to lecture 3, which it is after all lecture 3. So what I've tried to explain to you is the details of the machines are important for performance. So I've told you about processor hierarchy, processor parallelism that's sort of inherent in there, that what the memory system looks like. And the thing is that before you write parallel code, which you're writing to go faster, you should make sure you're getting good serial performance. I mean, most code runs at 10% of peak, even on a single processor, right? If you can get a factor of 10 on the serial code, you want that factor of 10 too, in addition to whatever you're going to win from the parallelism. So, and I've tried to tell you what to expect because of all these hardware limits. What are the relative costs of everything? So just to give you a matrix multiply example, when we hand you the code for your homework, for homework 2, the naive code runs at 2% of peak, right? So there's a factor of 50 that's possible. If you do the simplest optimization that I described, the blocking, which is actually the code that we'll hand you, it goes 7 times faster. That's a whopping 14% of peak. Now, by the time you add all these other optimizations, you get another factor of 6. You can get up to 84% of peak, right? You want both the factor of 7 and the factor of 6, right? They're both important. And so that's why we're doing this for the first assignment. We also talk about how much parallelism there is hidden inside processors by pipelining and SIMD. We talked about memory hierarchies and that it costs hundreds of times as much to go to memory as to just get it out of cache. And there are 2 kinds of locality to worry about: temporal, which is to reuse the data that you've recently used. And there's also the spatial stuff, which refers to the fact that when the machine goes off to memory, it doesn't just get the one word you asked for, it gets a whole bunch of adjacent words. So you should organize your algorithm to use all that adjacent stuff as well. And our goal over many parts of the semester will be to minimize communication or data movement. So that's the end of lecture 2. And I just want to say a few words about class logistics before I go on to lecture 3. But are there any questions about this low-level stuff? In the microphone? Did we have a question in the front row? Sorry, just want to make sure that everybody can enjoy the question and possibly the answer.
So with moving data around, that's 2n cubed operations, I would presume, right?
So if you do it the naive way.
Okay.
And that's if you write the naive 3-nested loops, you will move the data 2n cubed times between fast and slow memory. But by doing it this way, you can reduce that by a factor of the square root of the cache size. And if your cache is, 1 million words, then that's a factor of 1,000. That's a good reduction.
Okay.
Right. Is that okay? Any other questions? So let me just say a few words about logistics. So homework 0 is posted. It's been there for a while. And just to remind you of what it is, you should just pick your favorite thing you'd like to do in parallel this semester, right? It could be, I want to, predict the climate, or I want to, optimize a particular code. Whatever you like, just describe what you, in principle, like to do. And what we want to do is post these in part so that you can find partners for class projects, right? So, you can work on your own if you like, but if you want, maybe there are 2 of you who are interested in the same thing. How are we going to discover that in a class this large? Well, that's what that's for. And that's due Friday. Hopefully people can do that. There's also there's an online class survey, so we can find out about your programming background, so we can assign teams for homework 1 to make sure that there's a mixture of experienced programmers and people who maybe need a little help to get up the learning curve and all these details. So that's the plan there. And then we'll assign teams for homework 1, and then we will post it. There's a lot of reading material, and I invite you to go look at it. But so certainly people have written very many detailed surveys of how to do these kinds of optimizations, and I've just given you a high-level view. Okay. So let me go on to lecture 3. Finally, we get to parallelism. And so what I'm going to do is give you, again, this is going to take 1.5 lectures. I'm going to give you an overview of parallel machines, both what the hardware does and how you express parallelism on top of them, which is, to some sense, a little bit tied to the architecture. So there are going to be a number of different kinds of parallel machines that I want to talk about from both the hardware and the software point of view. The simplest kind, or let's say the original kind, which is probably in all of your laptops, is shared memory. So what does that mean? That means when any processor says, please go get location 37, it means the same thing. There's one sort of global address space that everybody uses. And the trouble with that is that you can't scale that up to thousands, let alone millions of processors. But that's certainly the most common kind and easiest to use. The next kind of parallelism is going to be shared address space. So that gives you the same impression that when you say, please get location 37, everybody sees the same thing, but it's actually not shared. There's an interesting layer of hardware that makes it look like it's shared. And people have built those because people like to have shared memory, but it also only scales up a little bit. Then we'll talk about message passing. That's what Hopper and Edison and all the biggest machines in the world look like. They give up on the idea that you can share things. If two processors want to communicate, they have to send one another messages. And so there will be you'll have to send, it's like the post office. You'll have sends and receives, and you have to have a separate network that communicates. There's also data parallelism, and that's been around for a very long time. We've seen it already just in those SIMD instructions where you can do 2 or 4 operations at the same time. But if you have a GPU in your laptop, you can do thousands of things potentially. It looks like you're doing thousands of things at the same time. So that's another natural kind of parallelism. Now, it turns out that the really biggest machines are clusters of all these things. They're hierarchical hybrids of all these combinations. So the machines that are on the top of the top 500 list, they do message passing. But if you look inside each particular parallel computer, you may have another cluster inside of that. You may have shared memories. They may have GPUs attached to them. So it's really quite a mess to program these things. So you have all of these different models are there at the same time. And then finally, there's all the computers in the world connected over the internet. I'll call that the grid. And people actually do use that for computing. And so maybe the first and most famous example is SETI at home. So have people seen the movie Contact with Jodie Foster? So this was sort of the predecessor to that. So you can sign up your computer, if you have spare cycles, to download inputs from radio telescopes and download code to look for signals from aliens. And if you find one, you'll maybe get to have be in another movie. But thousands of people around the world have signed up to do this, and it's an embarrassingly parallel task. It all runs over the internet, and so that's yet another level of parallelism. But that's probably the biggest parallel computer in the world. Historically, whenever somebody came out with a new computer architecture, some architect had a new brilliant idea, they invented a new programming language to go with it, so you could write code that went as fast as possible. Needless to say, this was not popular among users, that they had to rewrite their code completely every time a new architecture came out. Today, and for a long time, portability has been more important. So the languages that we'll be talking about here have been designed by committees, for the most part, so that they are standardized, and so that when you write a program today in using the standard message passing library, which is called MPI, the chances are excellent that it will run 5 or 10 years from now. Maybe not as fast as you would like, but it will be portable. And so that's sort of the history of things. So here is sort of the cartoon to have in your minds as we talk about all these different parallel computers as to what they look like. There's a whole bunch of processors. There's a whole bunch of memories. And connecting them all, both processor to processor and processor to memory, there's an interconnection network. And all of these different machines are going to look different, but at this level, this is what they look like. So one of the questions you should ask yourself when you hear a new architecture is, where is the memory actually physically connected? So it could be the memory is actually attached to each processor. So each processor can look at its own memory very quickly, but it has to go through the interconnection network to get to another processor's memory. Or it could be that no processor has anything besides a little bit of local cache, which it can see. To get to any serious memory, it has to go through the interconnect network. That's certainly a possibility. And the other question is, what does it look like inside here? The cartoon we've used so far is that there's one wire, or maybe several parallel wires called a bus. And everybody, one person can talk at a time, but everybody's connected to it. That doesn't scale up very far. And so real interconnection networks are, have some sort of graph structure. You may be, for example, a torus. You may be connected to your north, south, east, and west neighbors. And messages have to get forwarded from one processor to another until they finally get from the source to the destination of a particular message. And there's a lot of innovation that's gone on over the years as to what the topology of these networks should look like, who should be connected to whom. And there's just been a big wave of innovation in that too. And so, for example, Edison has a different interconnect network than Hopper because Cray decided, there's a better way to do it. So there's a bunch of innovation going on there. So they went from a torus to something called a dragonfly, which we'll talk about later. So here are the programming models that are going to go with all of these. Or I should say, here are the 3 questions that any programming model is going to have to answer in order for you to program effectively. The question is, how do you control parallelism, where's the data, and how do you synchronize between different parallel things that happen at the same time. So the programming model is basically the languages and the libraries that create the abstract view of the hardware and let you do these three things. So control is very simply, how do I decide that I want to do two things at the same time, or 4 or 8, and how do I decide when they're all done, and I want to say, compute the sum of all the results that they computed, right? So in what order do they happen? That's control, and I'll have concrete examples. Then there's the data, and as I mentioned, there's two different kinds of data. If your program says for I equals 1 to 10, you would like the value of I to be yours. You would not like someone to come in the middle of your loop and change the value of I. You would like that to be private. And so, and we will show you what happens when I changes. It does happen. So we want to declare some variables to be private, and we want other ones to be shared, because there's no way to run a parallel program and collect, that's interesting unless you can share some data. And so how do we distinguish between private and shared data? And and then how do we actually communicate it from one processor to another? And then there's synchronization, because if we have a whole bunch of processors going on at the same time, they're probably going to have to decide, who goes first, who has which value, how do I divide up this particular task if you do it dynamically, so we have to coordinate that. And that's going to depend on which operations the hardware supports as being atomic. So let me give you an example. Suppose you have a line of code that says s equals s plus 1. So very simple line of code. So what does that turn into in assembly language? You have to get s from memory, put it into a register, you add 1 to it, and then you put it back. So what if I get s from memory, and then some other processor who also is trying to do s equals s plus 1, that processor gets s from memory, so I have two values of s. We both add 1 to it, and then we put them both back, and I've lost one of my plus 1s. Right? So that means that s equals s plus 1 is not atomic. So what is atomic? That's the only thing you can sort of count on to reason about your program. And I'll have examples. And of course, how much does it all cost? So the example I'm going to use to illustrate these different programming models is going to be this very simple thing. I have an array of numbers, A0 through AN minus 1, spread out over the machine. I want to compute some function of each one and compute the sum. So the question is, how am I going to do that very simple map-reduce algorithm, if you like? If you've done cloud computing, this is a canonical example. So I want to compute a function, a map, and then do a reduction, compute the sum of everything. So the question is, where does A live? Where is the original array? Is it all in a single memory, as it might be in a shared memory machine, or is it partitioned across a bunch of processors? How do I decide which processor is going to do which fraction of the work? And then how are they going to coordinate so that everybody can agree on the single correct sum at the end? And so if I were to write this in MATLAB, I would write 3 lines of code, just to sort of give us a sense. So there's the array A, and that represents one array of data. Then I want to apply the function f to all the entries and get another array. I'll call it fa. And then to do the reduction to one number, I need typically some function which does the coordination, and that's built into many libraries, including MATLAB. I just want to do the sum to get one number out. So that's what I want to do, and the question is, how do I make that happen? So let me start with the simplest sort of programming model, which is shared memory, so the multi-core chips in your laptop. And so the mental model is that a program is a collection of threads of control. And so you can think of a whole bunch of subroutines, perfectly sequential subroutines that are all running at the same time. Each processor is running its own sequential subroutine, and each of those is called a thread. And we'll see later how those get created. You could imagine you have one main processor, and it calls a bunch of subroutines, but that subroutine could then be executed in a different processor. I'll show you what the syntax looks like. So one processor could say call function 1, call function 2. Function 1 moves off to another processor and starts running. Function 2 goes off to another processor and starts running. Each of those are called threads. So each thread is going to have some private variables which are declared locally inside that subroutine, inside that thread, like for I equals 1 to 10, I is yours, it's private. And those, for example, in C, those are going to be declared in your local stack. So whatever you declare locally. And there's also going to be a set of shared variables, so we can coordinate among these things. And those could be, for example, static variables declared in the main routine. And if you were in Fortran, it would be a shared common block, or you could have a global heap, if you do that. And so the simplest C program would declare some variables, and then it would call the threads. And the threads would be able to see those global variables. And so how are the threads going to communicate? They're going to do it by implicitly by reading or writing those shared variables. So that's how they're going to send data back and forth to one another. And they're going to coordinate by synchronizing on those shared variables. They're going to have some of these variables which are sort of flags to say who gets to go first. And so here's kind of a cartoon of what the memory is going to look like. I have n+1 processors. Each one has some private memory. So the stuff that's orange here is the values that are only visible to processor 0. So when processor 0 refers to variable I is 2. When processor 1 refers to variable I, it's 5. Nothing to do with one another. Up here is the shared memory. So these are the variables that are declared statically. So when processor 0 says y equals s, it will go off into the shared memory and get the value of s and bring it back, and it will have a copy here. And when processor n says s equals something, it will go take its value, whatever it is, on the right-hand side of the equal sign and put it off into the shared memory. And so if this line of code goes first and then this line of code goes second, y will get whatever value was stored over here, but it could happen in a different order, right? And getting the order right is one of the things we'll worry about. So let's talk about how to add up n numbers. And so let's suppose that I have a relatively small number of processors compared to the number of array entries, so that it's worth using all the processors. So every processor is going to have n over p numbers assigned to it to do the work. And so my one thread is going to have the job of computing n over p of these function calls and computing the local sum, the partial sum of those n over p numbers. And so here's a simple picture, 4 threads, 16 numbers. Each one gets 16 divided by 4 to compute a global sum. And so what's logically shared are the original array of numbers everybody could potentially see. And the global sum, which I haven't computed yet, that's also going to be globally shared. And what's going to be private are all of the function values, so f of a0, f of a1, and so forth, and these partial sums. Well, let's see. Should the partial sums be private or not? Let me try to write some programs to do this, and we'll see that they're buggy, and then we'll eventually debug them. So here is sort of the simplest code you could imagine writing. Suppose I have 2 processors, and the first processor is going to sum the first n over 2 array entries, and the second processor is going to sum the second half. And the way typical code looks like is I have a subroutine called sum, and I have a function call called fork. And what fork says is, please execute this subroutine on this input data on some processor. And some processor will go off and do that. So that starts a parallel process on a different processor. Then the next line of code says, now on this subroutine, I'm going to execute the same subroutine on this other subset of the data. So this generates 2 things going at the same time. So let's just ask ourselves what happens when we run this kind of toy code. And so I'm going to have a static variable, which everybody can see. It's declared s, the sum, to be initially 0. And so thread 1, here's this subroutine called sum. And it does the obvious thing. It's going to loop from 0 to n over 2 minus 1 and increment s by f of I. And thread 2 is going to do exactly the same thing, except it's going to do it on the second half of the data. And these are going to run in parallel. So the question is, what is wrong with this program? Do I get the right answer? And obviously not. Well, for some people, obviously not. And for some people, it looks OK to me. The answer is there's what's called a race condition, or a data race. So these 2 processors are grabbing the same value s, and they're not synchronized in any which way. So for example, thread 2 could grab s and get a 0. Thread 1 could grab s, get a 0. Then they just keep their local value of s and compute the local sum. He computes the local sum. And then they put s back. And if thread 2 goes first and thread 1 goes second, none of these guys are going to show up in the value of s. So the question is, what are we going to do in order to fix this? So let me just show you what all the possibilities are. There's actually a combinatorial explosion of different answers you could get from this program. So let's suppose I just have 2 numbers that I want to sum. So my array is of length 2, and my function f of x is x squared. So what I really want to do is compute 3 squared plus 5 squared. Let's just see what we could possibly get. And so now what I've done is I've taken these 2 threads and I've compiled them. I've written them out in assembly language. So all I'm doing is I'm getting the value of s from the shared value, and I'm putting it in my local register that's private. Then I increment the private value of s by the value squared. And then I put it back into memory. So let's just ask ourselves, what answers could I possibly get? All that we're getting, this is executed by one processor. It's sequential code. Each one of these lines of code is executed in order, no surprises. This is executed by a different processor, and they are also executed in order, but I have no guarantee of the relative order of these two, right? They could be, interleaved like this, or like that, or like that. They're all possible. So let me just give you one example. So let's suppose that he gets a sub 1, that's a 3, and he squares it, gets a 9. He goes and gets 5, squares it, gets a 25. Then processor thread 1 goes and gets s, gets a 0. Then that processor goes and gets s and gets a 0. That processor then increments and gets a 25. 0 plus 25 gives you 25. Then puts it back in memory. So s is now 25. In the meantime, thread 1 goes and increments s in his local register and gets a 9. And then puts it back into memory. And so when you're done, s is equal to 9. It's not 9 plus 25, it's 9. So in fact, you can get any one of these three possible answers. You could have gotten the right answer, which is 34. You could get 9, or you can gotten 25. So the question is, what are all the possible answers? What are the operations that you can count on as being atomic, that they execute as though they were all alone in the world, and they can't be interrupted by anybody else? So reads and writes are indeed atomic. So when I do this read, register 1 equals s, I will get a value of s at some point in time. I won't get like half the bits from this cycle and half the bits from a second cycle. It's always, a completely well-defined object. And and when I do an addition, that's always correct. There's no question I'll get half the bits from one time period and half the bits from another time period. But this, something plus equals, so that's, s equals s plus something, that's not atomic, because it breaks down into all these different lines of assembly language. And so this is why these things can go wrong. So let's try to fix it. And so here is one attempt to fix it. Let's see if it does it. So now each of these threads is going to have a local private variable. And I'm going to sum all of the data, the first half of the data in this local private variable. No chance that thread 2 is ever going to ask for local S1, it's private. And thread 2 is going to have local S2, that's private. And so for sure, local S2 and local S1 will have the right sum of function values at the end. But then I still have to get together. I still have to put them together. And so this line of code and that line of code appear still. And addition's associative, so I don't really care what order it happens in. So is this better than the code I had before? I now only have one chance for a raise. I used to have n chances for a raise. So maybe it's less likely I'll get the wrong answer, but there's still a raise condition here. I still could have that same problem. So what do I have to do? I need a new feature in the language, and it's there. It's called a lock. So what I'm going to do is, when I get to this point, and I want this next line of code to execute atomically, I'm going to knock on the door. I'm going to ask, is anybody there? And if not, I'm going to walk in and lock it behind me. And the lock has a name. And then I'm going to execute this all by myself, and I'm sure that nobody else is going to be in there to do it. And when I'm done, I walk out and I unlock the door. And if I get there first, and this guy shows up after I've gone in and he says lock, he's going to have to wait. He's not going to be allowed to go in until I unlock it and goes in. So this is going to be executed in an atomic fashion, all alone. So that works just fine. So, but you may ask, why didn't I just put this lock inside the inner loop? Why didn't I just go back to this code here? Let me go back. And just put a lock, unlock, lock, unlock there. What? It would have been correct, but it would have been incredibly slow. It would not be parallel code anymore. It would be sequential code. I'm only doing one add at a time. I don't want that. So that's why I need to lock as infrequently as possible. A lock may, in some instances, be a call to the operating system. It may cost you thousands or who knows how many additions, and so you certainly don't want to do it very often. This lock has a name. You can have multiple locks with multiple names. You can have arbitrarily complicated kind of patterns of communication and locking. Okay, so this is how far I've gotten. I've talked about the programming model, which is shared memory. And my goal, I won't finish it all today, is to do everything else here. So what I'm going to do next is talk about the machine models that people have built, the hardware that implement that shared memory programming model that I just showed you, and what the hardware people have to enable that. Then I'll talk about message passing, which is what scales up to thousands or millions of processors, and where you have to have subroutines to do sends and receives, as opposed to simply referring to shared variables. And I'll talk about a little bit about the hardware that people have built for that. And then there are people who want the best of both worlds. They want to write shared memory code, but they want to run it on big message passing machines. And so I'll describe their attempts to make that work. I'll say a little bit about GPUs, parallel, and finally the fact that the really biggest machines combine all these. And so you have to program in all of these at the same time, alas, if you want to run the biggest machines in the world. OK, but let's go back up here. And I have time to just go through, I think, these three. So all these shared memory platforms. So this is the simplest version. It's the multi-core chips in your laptop. And all the processors are connected over a shared bus to a memory. So here, the $ means cache, obviously. So each processor has its own private cache. And if you refer to a location which isn't in your local cache, it will be sent over the bus, and you'll get it in the shared cache. And if it's not there, you go to memory. And so many companies have built these things over the years. And in multi-core chips, you may have several levels of cache that are private and several levels of cache that are shared. These are different decisions that architects make at these different companies. So the advantage of this is that you don't have to think about how far away something is stored. If it's either going to cost a constant amount to get it locally or a constant amount to get it far away. So it's called uniform memory access. So every memory item costs the same amount. Once you go to the bus and you go here, it's not like different locations cost you different amounts. Obviously, some architectures are going to do that. So the trouble with this, it's a perfectly natural way to do it, is that it won't let you build very large parallel machines. 32 is the biggest people have typically built. And why is that? There's this shared hardware resource. So everybody is communicating over this one shared thing to get to the shared cache in the memory. You can't have an arbitrary number of processors here, or this becomes a bottleneck. It's nice and simple and convenient, but it doesn't scale very far. OK, so that's just what I've said. And one of the reasons you can't scale it very far, let me just come back to this, is something called coherence. So suppose processor 1 loads location 37, and processor 2 loads location 37. They get independent copies of it in their local caches. And as long as they both just keep reading that in some loop, they're very happy. It runs really fast. But now, suppose processor 2 writes location 37. So what happens to the copy that processor 1 had? It's now out of date. How does processor 1 know that it's out of date? There's some communication that has to happen. There has to be some coherence, that's called coherence protocol, that this bus has to tell everybody, oh, if you happen to have location 37, you better say it's dirty. Set a dirty bit, that it's not good anymore, that something else, that there's a new value that you need. And the next time you read it, you're going to have to come and get it. Right? So that's why it doesn't scale very well, because you need a lot of hardware support to make that happen. So let me give you some performance data just to show you what goes wrong. And this was some work done by Pat Worley at Oak Ridge, where he took an embarrassingly parallel piece of a global climate model. So this was simulating water, oceans. And he said, well, I'm just going to run many, many copies of it on independent data. So there's actually no sharing whatsoever. So it should be like the perfect scalable code. I'm going to put it on a shared memory machine. I'm going to make it on larger and larger models, and I'm going to see how well it scales. So in other words, he's going to start with a small model of the oceans and then do a finer resolution with more data. But it's all disjoint, so in principle, it should all scale perfectly, right? There's no data sharing. And so let's just sort of take the measurements and see whether this particular shared memory machine does that. And so here's the measurement, and this was on an old IBM 690. So the horizontal axis is the size of the model. So these are different terminologies for the size of the grid. So this is a very small model. That's a very big model. And the vertical axis is the speed per processor, the megaflops per processor. And for different numbers of processors each line. So a perfect scaling would be as I increase the number of processors from 1 to 32, since they don't share anything, 32 processors should run just as fast, 32 times as fast as one processor. In other words, each processor should individually run as fast as one processor, and that's almost true. So one processor runs that fast. When you take 32, each processor runs at almost the same speed, so you're almost going 32 times faster, which is what you want. Now let's make the problem bigger, so big that it doesn't fit in the local cache of each of these processors. So that means if I go back here, that my local climate model no longer fits there, it has to be put out here. So even though this processor 1 and processor 2 don't share any data, they have to go over the same bus to get to their disjoint climate models they need to run. And so what happens when you do that? Let's go up to the biggest climate model. So when I go from 1 processor to 8 processors, each processor slows down, by some significant amount because they're sharing that bus. And if I go up to 32 processors, it slows down even more. So that's sort of the limit of scaling for this kind of stuff. Even though this is embarrassingly parallel, they shouldn't share anything at all, it still is sharing the bus. So there's some hardware sharing going on. Okay, so obviously people build different architectures to deal with this, but that's the limit of the simplest kind of multi-core architecture. So here's another machine model that people have built, and this is called a multi-threaded processor. In this case, I have multiple thread contexts. The model I had before is a thread was like a subroutine, and you thought of it as owning a processor. There was a one-to-one correlation between threads, subroutines, and processors that they ran on. It doesn't have to work that way. It could be that one processor has as many as, say, 8 threads that it could run. So this, for example, a Niagara, this is a fairly recent Sun processor. It could run 64 things at the same time on 8 cores. How did it do that? Each core was assigned 8 threads. It could only run one at a time, but it could switch back and forth between them in one cycle. So the idea is it starts running one of these threads, and it goes on for a while until this thread says, oh, I need something from memory. So it's going to wait. What does the processor do? Immediately in the next cycle, it goes to the next thread, the next subroutine, and starts executing it. And so it's never idle. And when the second thread gets to a memory read or write, it stops, and it goes on to the third thread. And so hopefully by the time it gets to the 8th thread, the first thread is ready to go again. So the processor is always busy, and it needs this, because it can switch back and forth between different subroutines, in one cycle. And so obviously you need extra hardware to make all that happen. But this was a popular thing. It was good to avoid getting stuck by slow memory latency. And there's some larger, older machines built by Cray for high-performance computing that were also done like this. So here's sort of a picture of how things might have been assigned. So imagine that you have 4 different programs, and each program in turn generates multiple parallel threads. So this program might have n different things it could do at the same time. This program may have 2 different things to do at the same time. This one would have n plus n small ones and 1 big one, and this is a sequential program. And on a particular platform, you may have 4 things that could go on at the same time. So 4 cores. So this core may be executing parts of these n may be assigned to it. It may get some of the red threads. It may get some of the green ones. The blue one is sequential. It only runs in one place. And there are only 2 things that happen in parallel of the yellow thread, thread 2, so it happens there. So the hardware was doing this for you all automatically. And again, this scaled with limits. But Cray still built that machine and sold a few. So the last one that I want to mention is distributed shared memory. And it still has a shared memory flavor. So when I load location 37, it means the same thing everywhere. But this has let people scale up to 512. That's the biggest they've managed to get here. And so now they have to have a whole lot of extra hardware so that when you refer to a location, it has a table that says where it is stored in the machine. Where is this particular cache line stored? And so if you ask for location 37, it's not in your cache, you have a local table of where to go look off in the rest of the machine to go load it. And so there's an enormous amount of extra hardware required in order to avoid sharing everything. But it's managed to scale up to 512. And so and this network is not a bus anymore. You can't build a bus with 512 things attached to it. It's usually a torus or something else where you're only connected to a few nearest neighbors. And so anyway, that's been done, but it has its limits too. So at this point, we've gotten to the end of machine models for shared memory, and next time I will talk about message passing in distributed memory, which is what the real big machines are. So any questions? Yes, there's a question back there, and there's a microphone coming your way.
So a lot of the time on these machines, I'm guessing there's typically some sort of operating system that's running in the background. So if we have things like an L1, sorry, an L1 cache or an L2 cache, things like that, then presumably parts of it are being used by other programs.
So that's a good question. And for very large high-performance computing, they build stripped-down operating systems because they don't want very much time to be spent there. And the scheduling that the operating system is allowed to do is very much limited so that it can't swap programs in and out. So if you're on a, and that's true on the high-performance computers like Edison and Hopper that you'll be using. For other clusters, then yes, there's a lot of operating system noise. And in fact, one of the interesting data measurements that I'll show you later in the semester is that the operating system causes some processors to end much later than others. And so you may have, your program may run dramatically more slowly than you would have expected, because even though every process was assigned an equal amount of work, somebody got swapped out for a while, and everybody had to wait for the slowest one. And so, but people work hard on making the operating system special, so that doesn't happen.
So say that I'd like to take a lot of the stuff that we've learned today from like the instruction level parallelism, stuff like that, and say take my MacBook Pro and try a couple of experiments out. Like, can I expect the same types of performance boosts, and like what would I have to change?
So that's a good question. I think that given, if you're surfing the web at the same time, no. So I'm not. So you'd have to make sure that everything is quite idle, and that's a good question. I think I'm going to have to take offline because I'm not sure what features on the MacBook Pro would let you turn off a lot of other processes and let you do an experiment like that, which is one of the reasons we have accounts up on Hopper, which is a much more controlled environment.
Does this mean if I run experiments on my MacBook Pro, I should like not browse the internet or do anything else?
Yeah, so you can certainly do debugging of all of your homework assignments on your laptop, because all of the software tools are meant to run in general locations so that people can debug wherever they happen to be sitting. But the performance data probably won't make a lot of sense until you run it on the real platform. So I should add that within the Parlab, and there was a fairly large operating system activity to say what features do you have to add so that you can allocate a subset of the machine and be guaranteed that you get it for the duration of a particular run and not get interrupted. And so I can give you some pointers to the tools that people built there, but that's been a recognized problem for some time. And so I don't think that's incorporated in your MacBook Pro. That was a research project over the last few years.
Okay, thanks.
Okay.